Now here is the main thrust of all of this discussion about vectors that we've been doing in the mathematical framework, right? We learned what a vector is. It points in space, has a magnitude and an angle to an axis. Then we learned that we can break any vector up into an x component, a y component, and a z component if there is a z component. And then we learned about unit vectors to write those vectors down in a mathematical notation in terms of the unit vectors. This is why we're doing it. This lesson puts it all together. Because in most physics problems, there's usually more than one vector happening at once. And we already know that a lot of times we want to add these vectors together. The best example would be the concept of a force. I mentioned many times we haven't gotten to our lectures on force, but you know that a force is either a push or a pull. And if I have, like, for instance, an airplane, there's many forces acting on an airplane. You have the weight pulling down, that's a force acting on the airplane. You have lift pushing up on the airplane, that is a force. You have thrust from the engine, and you have drag from the resistance of the air. Those are two more forces, so now we're up to 4 forces. And then you may have additional winds coming from different directions. You may have any number of things going on, pushing that airplane or pulling it around. So when we analyze a situation, we have multiple vectors, in that case forces, but it could very simply be multiple magnetic fields acting on something. Multiple vectors, right? Because a magnetic field is a vector as well. What we usually want to do is add those vectors together to resolve it into a single force, equivalent single force acting on the airplane. So instead of 4 separate forces, if we could somehow add those vectors together, then we could replace those 4 forces with a single force, acting in a specific direction with a specific strength. And that single force would be the vector sum of all of those other forces, and it could sort of replace, in an equivalent situation, just the individual forces with a single force. And then it's much easier to solve if I can resolve everything and add everything and get it into one single force. So we want to add them together. And we've tried graphical methods. We know how to add vectors graphically, but it's a pain. So here we're going to add vectors together. So let's talk about that. Let's talk about the concept of a force, which we're going to get into more detail later, but force in physics is a push or a pull acting on a box. In fact, let's consider not one force, let's consider 2 forces acting on a box. So instead of just drawing a box in a vacuum, what I'm going to do is I'm going to superimpose this box on an XY plane. I can put any coordinate system anywhere I want. And here, I'm just going to say that there's a box where the corner of this box, this corner right here, is at the origin of the coordinate system. So what is this thing? It's a box. All I can draw is boxes and circles. So that's my box. And then I'm going to say we have some forces acting on this box. So let me put some tick marks here. Let me put some tick marks. So 1, 2, 3, 4, 5. So I'll put 5 right there. And then I'll have 1, 2, 3, 4, 5, 6, 7, 8. So 8 will be up here. And I'm going to put 2 right here. So this is just regular tick marks, XY tick marks. So what I want to do is I want to say, all right, I have not 1, but 2 vectors acting as a force on this point of the box, on the corner. Like there's a rope attached to it and it's being pulled. One of the vectors is pointed right here where the tip is at 2, 5, like this. Right, so here's one of them, or 5, 2. Sorry, 5, 2. And then this would be vector, we're going to call vector A. And then the other vector is at 1, 8. And when I say 1, 8, I'm basically specifying the coordinates, basically the components of this thing. It's going to be really hard for me to draw a straight line up here, but I'll try. Please forgive me. It's not going to be perfect. That's not perfect, but you get the idea. It's a straight line going up there to 1, 8 right there. So my question to you is, this is the real situation, and this is vector B, like this. In real life, if I had 2 different ropes attached to a box, and I'm applying forces by pulling on those ropes, and these forces and these ropes are arranged like this, where one of them is very steep and one of them is very shallow, and I'm pulling harder on this rope than I am on this one, that's why this arrow is shorter. Now, the box is only going to move in one direction. We know that if we have 2 simultaneous pulls, the box is going to move at some angle, and so on. But what I'm trying to say is, the real world, there are 2 forces acting. But if I could add vector A and B together, to arrive at an equivalent vector, which is the sum of A and B, then I could replace the situation with the box with the single force acting, and the single force acting at a certain angle would be equivalent to these two forces acting. In other words, if I did the experiment twice, one with two ropes, two forces, and the other with the vector sum, single force, then the box would move the same way. And so that's how we know they're equivalent, because I believe you would agree that the box is going to move some sort of way. If I could find the equivalent force where it's a single force acting to make it move the same, then for all practical purposes, these two forces are equivalent to a single force. How do we add them together? Well, we learned how to do that before. We could slide vector B over. This is tail to tail, so we don't add them there. We move it head to tail over here, and then once we get it over here, we draw from the tail of one to the head of the other. That's a graphical method. We don't like graphical methods because they're not accurate. It all depends on how nicely and neatly you draw your picture. Here's what we're going to do instead. We're going to write down vector A and vector B in terms of their vector notation. So vector A is going to be what? It's going to be 5 in the I direction plus 2 in the J direction. How do I know that? We've already covered this in the last lesson, but we know that because if we look at the components of A, here it comes and touches right there, and over here it's touching right there. So the x component in the of A, the x component is 5 units. So it's 5 units in the I hat direction. Remember, I hat is just a unit vector of length 1 pointed along x. So when we take 5 times that unit vector, it just makes a longer vector in the same direction. So it's a component which stretches all the way from here to here, right? And then in the y direction, it's 2 units acting multiplied by the j unit vector, which is the unit vector that's 1 unit long. So it makes a vector 2 units long there in the y direction. So this is basically the component down here is a vector, and this is the component here as a vector. 2 times j, 5 times I, all right? So then what we could do is we could say, let's do the same thing for the b vector. The b vector's coordinates of the tip would be 1 in the I direction, and then 8 in the j direction. We add them together, 8 in the j direction. Now, usually we don't write 1i. When the coefficient is 1, we just drop it. And so basically, we just call it I plus 8j. And you know that there's a coefficient of 1 right there. So what we want to do is then say, so if this is A and this is B, then what we say is the resultant vector, we call it R. The resultant vector is a word that just means you add them together and you get a result. The resultant vector is going to be the A vector plus the B vector. Now in the past, the only way we knew how to do this was to graphically move it and connect a line, and that would be it, the new vector. Here what we're going to do is we're going to take the vector A and replace it with what we just wrote. I'll put it in parentheses to keep it separate. 5 in the I direction plus 2 in the J direction. And then we're going to add to that a new vector, which is B, with this one right here. I, which is 1 in the X direction, plus 8 in the J direction. Now here's where the magic happens. These parentheses really aren't necessary because I can drop them effectively and just write everything together. I'm just doing it to show you this is vector A and this is vector B. What we are going to do is treat this like an algebra expression. How do you add things in algebra? You know, when you have 8x plus 2x, you can add them because you have the same variable x. When you have 5y plus 6x, you can't add those because one's an x variable and one's a y variable. Same thing with vectors and unit vectors. You can only add them if you have the same unit vector, right? So what you do is you say, well, here's 5 in the I direction, and here's another 1 unit in the I direction. I can add those together. So that's a total, if I can write correctly, that is a total of 5 plus 1, which is 6 in the I direction. And then we're going to add to that, this is a j hat, this is a j hat. So these are both existing in the y direction. 2 plus 8 is 10 in the j direction. Now notice that we could do this without any picture. The only reason I drew the picture was to let you visualize this, right, and give you a real example. If instead I just told you vector A was this and vector B was this and add them, all you would do would be add the I components, and 5 plus 1 is 6, and you would add the j components, 2 plus 8 is 10, and you would attach the unit vectors to them, and then you would circle it. There would be no need to draw anything, no need to translate one head to tail, no need to draw the resultant and measure anything. You literally write down the first vector in component or in unit vector notation. You write down the second vector in unit vector notation, and you add them. But the rules of math are such that you can only add things that are like terms. And in I-hat, terms can be added to I-hat terms. They are vectors that exist along the x-axis. So let's think about what we're actually doing when we add these things together. What we're saying is that this vector has, or can be thought of as the 5 units, or a vector of length 5 in the x direction. That's what this is. And this vector has a x component of a length of 1 in the x direction. Now the reason we can add them together is that when things are lined up, when forces are lined up, or velocities are lined up, or what other vectors? Displacements, when they're lined up in the same direction. Notice here is a head and a tail, here's a head and a tail. When they're lined up in the same direction, of course I can add them, just like numbers. If I have 3 newtons and 1 more newton and they're in the same direction, of course it's 4 newtons in that direction. It's only when there's an angle here I can't just add these numbers. But if they are lined up in the same direction, any vectors can be added together. The numbers can be added together if they're already in the same direction. So by breaking up vector A into an x component vector and a y component vector, and by breaking up vector B in an x component vector and a y component vector, then what I'm doing when I add them is I'm adding the x component of vector A to the x component of vector B, which are in the same direction. So if these are forces, this is telling you that I have a force along x of a certain amount for A and also a certain amount for B, and I can add those and arrive at an answer for the result in the x direction. And then I can add the y direction vectors, which are existing up for B and up for A, and those are in the same direction, and I can add those together to get 10 like this. And that is way, way, way easier than dealing with angles. You see, we don't have any angles anymore because, yes, there is an angle of the vector here, but when we break it into components, which we do with trigonometry, once we have it into component form or unit vector form, then we just add the x components and add the y components and add the z components, and then we're done. And we just write down the answer. This is the vector. Now, I need to remind you that any vector, whether it's written as a unit vector or just in terms of components, you can convert it back to magnitude and angle. This has a x component of 6. This has a y component of 10. How would you, if I wanted you, how would you convert this to find its magnitude and its angle? Well, the magnitude would be the Pythagorean theorem. 6 squared plus 10 squared. We add them together. We take the square root. That's going to give us the length of this vector, right? The angle will be the inverse tangent of y over x, 10 over 6. So you would take 10 divided by 6, inverse tangent, that gives you the angle. And then you have to make sure the quadrant is correct, but that's how you would take the unit vector notation, which is x and y components of the tip of the vector, and change it back, if you wanted to a magnitude and an angle. Because remember, any vector you can represent either way. This is the unit vector Cartesian xy way. Now let's see if this answer actually makes sense. Let's redraw this, and we're just going to see if it actually makes physical sense. So I'm actually going to erase this. I'm going to make this a little taller. You'll see why in a second. And let's let's try to add these vectors as if we were going to do it graphically. Okay, just for giggles. So let's put the same scale here. 1, 2, 3, 4, 5, and I'll go 6, 7, 8, 9, 10. Why not? And then I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. And what I'm going to do is I'm going to mark the same ones. 1, 2, 3, 4, 5. Here's 5 right here. Here's 10 right here. I'm going to put a 2 here. 3, 4, 5, 6, 7, 8. There's an 8 here. There's a 10 here. I'm just putting some numbers here so that we can easily identify them. All right, so how would we add them? The first thing, you would leave vector A alone. And so we're going to put it in exactly the same location, 5, 2. So the arrowhead goes right there. That's vector A, like this. What would we do for vector B? Well, in order to add them, we have to put them head to tail. So I have to grab vector B and move it over here. But notice to put the tail over here, I actually have to bring it here, but I have to shift it up also. So what's going to happen is, notice from here, I go 1 up and 8 over. So if I brought it here, I would have to go 1 over here and 8 up, and that would be coming up here to 10. So the original vector stopped up here at 8, but because I had to shift it up, the new one's going to stop up at 10, like this. So what's going to happen is it's going to go up. I think that's not quite far enough over here. It's going to be something like this. And then that vector is going to be like this, more or less, pretty close to it, right? And this is called vector B. So how would we add vector A to vector B? Well, now they're head to tail. I've just moved one vector over head to tail, and then I connect the tail of one to the head of the other, and that's going to be the resultant vector. And of course, I'm not going to be able to draw a straight line, but that is more or less what vector A plus vector B actually is. Now, what is that vector A plus B? What are the components of it? Well, we could just go down here and we could see that it's right here at 6. That's where it, I guess I could make it clear by just putting a dotted line here. Goes down right there, and then it goes across to 10. So what does this mean? X component of 6, Y component of 10. X component of 6, Y component of 10. So I guess I'm trying to prove to you, we're not going to do this every time, but I'm proving to you with the first example, that if you take two vectors, which you could think of as forces, two different forces acting on a box, or you could think of it as two different magnetic field vectors, or two different electric field vectors, which we'll learn about later, or two different velocities, or two different, there's many kinds of vectors, but two different displacements, whatever. But they're acting on, in a region at a specific point, essentially, and you want to add them together. What do? You put them head to tail, you draw the arrow, and the tip of that arrow is what we call the vector, and we write it down, the components, and we can write it as unit vectors. But that was tedious, and we had to make it all perfect and all this. But this was much easier. We just write vector A down, we write vector B down, and we add like terms. And then we put it down here. And then this is the answer. We don't have to graph it anymore because we know this is going to work for any two vectors that we add together, or any three vectors we add together, or every 16 vectors we add together. We just add all the components together individually. All right? Now, what about subtraction? Because we learned how to subtract vectors graphically as well. What if, instead of adding these vectors, I wanted to subtract them? And by the way, before we talk about subtraction, let me talk just for a brief moment about what this means physically. If there was a box here with two forces acting on it, where do you think the box would move? Well, if A and B were the same length, like let's say B was shorter, then we would guess that right in the middle would be the direction that the box would travel. But B is actually a little bit stronger, so that's going to skew the force a little bit more towards B. So we expect this box maybe to move up like this. Now look at what our vector's telling us. It's telling us that it's moving in that direction. The length of this thing is not quite as long as these two together because there was an angle between them. If I angle vector B more in the direction of vector A, of course it's going to be even stronger in the same direction, but this is going to give us an equivalent force such that if I put a box down here, right, and do this experiment 2 times, one time where I have two forces acting on it, how does the box move? I observe it. Then I put the box again and put a single force acting in this direction with a longer magnitude than either A or B individually, and observe how that box moves. These two boxes will move exactly the same. And that means that adding these two vectors together can make a simpler problem that functionally behaves the same as the original, and therefore, mathematically, it's much easier to do that. When we have multiple forces, we generally add them together to make the problem simpler in order to analyze it. Okay? That's the point I wanted to make. Now, we want to talk about subtraction. If we want to take A minus B, we talked about it, how to do it graphically before. To make minus B, we have to actually flip the vector B around to make the arrow down here, and then we add A plus a negative B. It was kind of cumbersome. But vector subtraction is dead simple now that we know how to handle it. Because if we take vector A and we would like to subtract vector B from it, what do we do now? First, we have to write down vector A. Vector A is, don't forget, 5i plus 2j. So we'll put it in parentheses, 5i hat plus 2j hat. This is vector A. Then we have a subtraction, and let's put vector B in place, I plus 8j. I plus 8j. So we're subtracting two vectors. We don't have to flip anything around. We don't have to be fancy or draw anything. We just solve the problem. Now these parentheses can come off. We don't need these. 5i plus 2j. But here we have a -1, and that is being multiplied in here. Now, we haven't talked too much about multiplication, but I'll tell you that when you take a vector and you multiply it by a number, all you do is multiply the coefficient. It's just like algebra. If you have 5x times -1, well, you multiply the numbers. It's -5x at that point. Well, you have the same thing here. This is just a unit vector with a 1 here, and then you're multiplying by the -1. And so what you get is -I, or -1 times I. And then this negative times the +8 is -8j. It literally behaves like variables in algebra. And now that we have these here, we can add the like terms together. So 5 plus a -1, or 5 minus 1, is going to give us 4i. And then the 2 plus the -8, or 2 minus 8, gives us -6, and that's in the j direction. And so we have a minus b, vector a minus vector b, is 4i minus 6j. Now, I'm not going to do it, but if you were to go here and take vector b and flip it around and then add the vectors, what you would get is a resultant vector that would be exactly 4i minus 6j. What the whole point of this is to not have to draw pictures anymore. So I'm not going to spend too much time drawing pictures. You have to kind of eventually trust the math to know that what you're doing is equivalent to drawing these pictures. Once you believe that to be true, which is what I tried to prove to you here, then from here on, you just add vectors in the easiest way possible so we can get into solving more complex problems. And here, when you subtract vectors, the only extra step is we had to sort of distribute this -1 in, and then we just treated it like normal addition in algebra, subtraction in algebra. All right? Now, what I want to do next is our last problem, and it's a little more complex, but it's not that complex. The problem basically says vector c has component c sub x is equal to 7.40, c sub y is equal to -3.80, and c sub z is equal to -6.10. And vector d has components dx 4.40, dy -2.00, dz 3.30. Determine the vector sum, or the vector components of the vector sum, resultant vector c plus d. We're adding the two vectors together, and we want to write down what those components are. So the first thing we want to do is write down the components given to us in the problem. And so we know that c sub x is equal to 7.40. We know that c sub y is -3.80. We know that c sub z is equal to -6.10. And we have another vector, d. We know the x component of this guy is 4.40. And then d has a y component of -2.00. And then we have dz is 3.30. All right, let me just double check before I go too much farther, make sure I didn't make any mistakes writing anything down. All right, and we want to add these, but these are just given to us in components. So what I want to do first is write down the unit vector notation of these vectors. What we will say is that the vector c is each of these components multiplied by their unit vectors. 7.40 in the I hat direction, minus sign from here, 3.80 in the j hat direction, and then a minus sign here as well, so -6.10 in the k hat direction. All right. Then we have vector d. So I'll write vector d with a hat on top, 4.40 in the I direction. Then we have -2.00 in the j direction. Then we have this plus 3.30 in the k direction. Now you see how already this is easier to deal with. Yes, you have to have I, j, and k, but it's better than c sub x and z sub y and c sub z. I mean, this is just cleaner because this is like one entity. It's like one object. This is all attached together, and it has all of the components in there with their unit vectors, so you don't have to write all these components over and over again to add them together. So the next thing we want to do is we want to add them. So we're going to say this resultant vector is equal to the c vector plus the d vector. Now, what you can do is you have two different ways in which you can do this. You can write a bunch of numbers down to get the point across, but I think you know from the first couple of problems what we're going to do here. We're going to add this vector plus this vector. So what's going to happen is we're going to add these together to give us the new I component, these together to give us the new j hat component, and these together to get the new k hat component. So what we're really going to have, I'm just going to effectively write the answer down because I don't want to write all these numbers over and over again. But when you take 7.4 and you add it to 4.4, you're going to get 11.8. But that is an answer in the I direction. Right? So you're just adding this, and it's in the I direction like this. Then you have the negative 3.8 plus a negative 2, so it's negative plus a negative. And so what you're going to get is a negative. And so 3.8 or negative 3.8 minus the 2 is going to give you negative 5.80. But that exists in the j direction, so we add those components together, or subtract them, however you want to think about it. And then the k direction, we have negative 6.1 plus 3.30, and so you get negative 2.80, but that is in the k direction. So I could have written all that down, you know, this plus this is equal to this, and this plus this is this, but it's just writing stuff for no purpose. I know at this point you have to recognize that adding numbers is something we can do in physics, right? And that the j plus the j is the j, and I'm saying it verbally, but that's what we're doing. So this is the vector representation of the sum. This is the vector. But the question didn't really ask for the vector. The question said, determine the vector components. And so when they ask for components, what they want you to tell them is that r in the x direction is this number, 11.8. And r in the y direction is this number, negative 5.80. And r in the z direction is this number, negative 2.80. So 11.8, negative 5.80, and negative 2.80. These are the components. Notice that this is just a number. It's a scalar. This is just a number. It's a scalar. This is just a number with the scalar. But when we take these numbers and we multiply by their respective unit vectors, we're building up from an x vector, a y vector, and a z vector fashion all the different components as vectors. When we add them together, we get the resultant vector pointing 3D space somewhere. So that is how we add vectors together. We have to teach in the beginning how to add them graphically, because if I don't teach you how to add it graphically, then you never understand how to do stuff like this. Because I use the graphical methods to prove to you that adding these vectors really was the answer that we calculated. So you have to know how to add them graphically. And also, when we do proofs of things later, we're going to draw arrows, and you'll have to know how to add and subtract vectors graphically. But we never use that to solve problems where we're trying to get a precise answer, because it's too crude. But from an understanding point of view, adding and subtracting vectors graphically is great. But from a mathematical point of view, when we really do it, we're going to represent these vectors in IJK notation, and we're going to add them. And when we add them or subtract them, we do it by components. Get the new vector. And if you want to bring these components out, if you want, then go for it. You can. So this, we would say, are the components, and this is the total vector assembled as a vector into three-dimensional space. All right, that was the first lesson on adding vectors by components. I'd like you to solve these yourself. We have several more lessons because adding vectors is so important. So follow me on to the next lesson. We'll continue to add vectors component by component. Learn anything at mathandscience.com.